Hello, welcome to our presentation on TLA plus specification of PCR parallel programming pattern. This is a work in progress. My name is Sergio Yovine, and I will be presenting this work together with Jose Solsona. We are both affiliated with Universidad Hort, Uruguay. This is the agenda of our talk. I will go through the main goals of our work and present the PCR, which is a parallel programming pattern. We are interested in modeling its semantics in TLA+. I'll go through it with several examples, and then Jose will take care of explaining briefly the TLA plus specification and get into the details of our work on that. Automated translator from PCRs into TLA plus to make this integration seamless. So let me first go through or introduce the PCR produce, consume, reduce pattern. This is what we call parallel programming skeleton. That actually encompasses several well-known programming skeletons such as MapReduce and others. And the idea is that the component is made of a producer, which can be think of as a one-to-many transformation, that it receives an input and produces a stream of data that are then consumed by a cascade of consumers. Each consumer itself is a one-to-one transformation, so it takes an input and outputs the same amount of data. And at the end of this graph, of the data flow graph, there is a reducer that is many-to-one transformation. It takes all data produced and transformed by the producer and the consumers and outputs a single value. Overall, a PCR is a one-to-one transformation. So basically, the data flow inside the PCR works out that we said. So each input is produced and generates. The producer generates a stream, and then the consumer reads the values, performs some transformation, outputs the value, and all values are then reduced to a single one by the reducer. So some important remarks is that the all reads are non-destructive. Okay, so any produced value by the producer or the consumers are there and are not destroyed after a read. So they can be read multiple times. No data produced is ignored. So every item must be read at least once. And then all these components, producer, consumer, and reducers inside the PCR work completely in parallel, only restricted by the data dependencies between them. So to be a little bit more concrete, we designed a language which basically has three components, which can be sort of assignments to variables, which are themselves streams. So the producer has this syntax P is equal to produce fx, where f is a basic function or another PCR, which is in charge of producing the actual elements, and x is just the input to the PCR. Okay, so P is what we call an indexed variable. That is, P represents the whole stream of data produced by the producer. Sec means that in some particular cases, the produce itself is a sequential process. Then the consumer is basically the same kind of thing. It has some function f, which is either a basic function or another PCR. The consumer and the producer and consumers allow nesting of PCRs. That's the way PCRs are composed. And the consumers take P, which is the produced variable, and output their data on C variable, which represents the stream of variables generated by the consumers. And then there is a reducer, reduce, which basically applies a commutative and associative operation that has some initial neutral value, V0, to the consumed or to the stream produced by the consumers to generate the final output of the PCR. So we said we identify variables PC as describing the full history of assignments, and then to denote a specific value, then we use sub-indexes. So PI is the ith value produced, and CI is the ith value produced by the consumers. Then the language allows for moving along the stream of data, performing either look ahead or look behind operations. For instance, if PI is the ith Fibonacci number produced by the producer, then in order to generate them, we can make use of the I-1 value and the I-2 value to generate value PI. This is like a look behind operator, but we can also apply look ahead operators moving forward on the string. So in order to operate, the producer requires defining an iteration space, which is also defined by the user. And the iteration space is defined by a lower bound, or an upper bound, and a step function that define all the indexes that need to be traversed during the computation. To illustrate the PCR concept, we'll go through an example, which is the count Fib prime. So it's a process for counting the number of Fibonacci primes in an interval. I will first present a first version and then a more a refined version of it that involves composing PCRs. So the first model is given by a producer that uses the Fibonacci function to produce Fibonacci numbers. And then consumers check primality on the Fibonacci numbers produced by the producer, and then a reducer basically counts all prime Fibonacci's generated by the consumers. So on the left, we have the abstract syntax of PCR, and on the right, we have its semantics. So in the syntax, we have just the functions, which are the basic functions. Fibonacci is prime, and just the count. Then the user-defined iteration space, the lower bound and the upper bound, and the step. So in this case, X is going to be instantiated by the number of Fibonacci numbers that we want to generate. And then the iteration space is the set of index from 0 to n. Then the Fibonacci primes PCR, Phi primes 1, has a sequential producer, go through the iteration space, and then produce the Fibonacci numbers. And then we have consumers that will check for primality, and then the reducer that will count. The semantics is given by this directed acyclic graph of dependencies, where P0, Pi, etc. are the indexed values produced by the producer. Here it says that to produce value Pi, the producer needs Pi minus 1 and Pi minus 2. C0 up to Cn are the values produced by the consumers, and we have a data dependency between C0 and P0, Ci with Pi, etc. These the computation of all these C values completely independent one on the other, so it can be executed in any order, and then at the end the reducer computes R, and to compute R it depends on all values. The reducer can perform intermediate computations and at the end output the final output, which is the number of Fibonacci primes in this interval. This is the basic model, the basic specification of Fibonacci primes, but the function is prime itself can also be parallelized. So we want to do that. In this case, we want to replace the function is prime by an PCR. And in this case, we need to, when we resort to nesting PCRs, we need to define an iteration space and the indexes of variables on a higher dimension space as lists of indexes. So we'll talk about the capital I is the iteration space of the upper level, and small I represent indexes in the iteration space, which is local to the actual PCR. All variables in the execution of a PCR are indexed by a multi-dimensional space that will represent as a list or tuple of indexes. So in this second version of the Fibonacci Prime counter, we expand as I said before, the is prime function here by PCR. Okay. So each time a consumer is executed, it will itself compute as a PCR, where the producer is the one that produces the device source. The consumer checks for whether it device or not. Reducer just makes the conjunction of all the outputs of the consumers. So basically, this slide, we have the same syntax as before, where we expanded is prime as a PCR, which is here from lines 21 to 26. It has exactly the same structure, and here we show the iteration space of the devisors. Okay, and on the right we see the same graph as before, where we have added more nodes here, which represent the data dependencies inside the is prime PCR. Okay, so D stands for the devisors, which we see here that are indexed with a couple of numbers. The first one corresponds to the index of the parent here C, and the second number corresponds to the local iteration space index of the PCR generated by the producer in the is prime PCR. And essentially the same kind of pattern of dependencies is shown as in the parent PCR. A represent the results of the reduction of the reducer in the S prime PCR.
Hello everyone, my name is Jose and I'm going to show you our TLA plus specification of the PCR concepts we have seen earlier. First, I'm going to discuss the high-level overview of our project. We organize our project across different TLA plus modules in a way it's convenient for us to handle. There is a PCR-based module. In this module, we have the principal definitions that we can find in every PCR. There is also a PCR iteration space module. In this module, we define some related concerns to the definition of iteration spaces. Every concrete PCR has its own module. It is called PCR followed by its name. In these PCR's modules, the principal actions P, C, and R corresponding to the producer, consumer, and reduction behavior are defined. There is also a main PCR module for the root PCR that is called main PCR followed by the name of the root PCR. There is also a type def module. In this module, we collect the basic data types that we expect to be in all the PCR modules involved in the system. So in a PCR, variables are stream indexed with multidimensional index, which are automatically generated by the underlying runtime system. We formalize this by using the concept of context and context mappings. So let var p type and var c type be basic data types. For the producer and consumer variables, we define var p and var c as functions from natural to records. In these records, the field B denotes the value of the variable at some assignment, and the field R is used to keep track the number of times it has been read. The value null means the assignment has not occurred so far. So a context represents the PCR state are in a scope. These are the components of the context. In is the input variable, EP is the current iteration index, BP and BC are the producer and consumer slide. Is the reducer result, and there is a state component, one of the possible 3 states for the PCR. Multidimensional indexes are modeled by sequences of NAT. A context mapping is a partial function from index to context. Any PCR have its own context mapping map. So map of capital A is the PCR context at some index capital A. For convenience, we give names to context elements, as you see here. We use record notation to denote the values at any index. We define also some useful predicates over output variables. Here we have written and read. Written holds true if a variable has been written at some index, and read holds true if some variable has been read at some index. Any PCR has associated an iteration space which defines the index generated by the PCR. For this, we define an iterator operator, which describes a range in terms of high-order operator, step, lower bound, and upper bound. These high-order operators correspond to the PCR syntax element discussed earlier. Every concrete PCR module describes its initial conditions by means of operator init context. Init context defines the initial context as a record with input value and EP set at the lower bound of the input X. BP and BC are initialized as not written yet. Red is initialized as a neutral value, and the state component is initialized as off. Every concrete PCR module also describes what is the possible next step as a disjunction of the actions. If the state is off, the only possible action is to start, but if it is running, the next possible actions can be PCR or quit. Quit is a convenient action that immediately terminates execution if the iteration space is empty. The main PCR module instantiates the root PCR and any other PCR involved. Here, the main system specification is defined. For example, let PCR1 and PCR2 be 2 instances of some PCR modules. Then the main module for PCR1, assuming PCR1 is the root PCR, will have the following form. So we see the init state predicate initializes the context mappings for each of the PCRs. The next step says that any of these 2 PCRs can do an action. Now we further illustrate our specification using the PCR Fib'1 example. At the left, we have the PCR syntax, and at the right, we have the corresponding TLA plus specification. Action P at some index always require the EP variable to be in the iterator and updates the context mapping accordingly. PP at EP index is set to the value computed by the basic function fib, and EP is updated to the next value according to the step function. For the consumer specification, we have a C action. It not deterministically chooses an A of the iterator for which BP has been written and has not been read, and for which the corresponding BC has not been written. And it updates the context mapping, marking BP as read and updating the BC value with the value computed by the basic function is prime. For the reducer specification, we have a R action. It not deterministically chooses an A from the iterator, for which BC has been written and has not been read, and it updates the current context accordingly. It sets the read component to the value computed by the basic function count, increments the read count on the variable BC, and update the state component according to predicate cdone. The cdone predicate holds true if every consumer variable on index other than A has been read. So now we are going to discuss PCR elements with nesting. PCR Fib'2 uses PCR isPrime as a consumer. In this case, isPrime is not a basic function. It is another PCR. First, we know that the producer at PCR isPrime sequential, so it's different from for the earlier one. In this case, it not deterministically choose an A from the iterator for which PP has not been written, and updates the context mapping, in this case map3. Now, for the consumer specification of PCR Fib'2, we have that the consumer call is split in two parts, call and read. In the first part, the action call, an index A is not deterministically chosen from the iterator, for which BP has been written, has not been read. So the current context mapping, in this case map2, is updated, marking BP as read, and the context mapping of the module isPrime is updated with the corresponding initial context. For cred, an A is non-deterministically chosen from the iterator, for which BP has been written and for which correspondingly PC is not written, and for which isPrime has finished. Then map2 is correspondingly updated with the value computed by the instance isPrime, and this is set in BC. Correctness and termination properties are specified in the main module. Our two previous PCR examples, Fib'1 and Fib'2, have the same properties. Solution is the expected behavior for this PCR. It computes all the Fibonacci prime numbers in the interval from 0 to some number x. So correctness is stated as forever if Fib primes have finished dead Fib primes out, that is the output of Fib primes, equals the solution on the variable n. N is the input variable of the specification. Termination is stated as eventually Fib prime has finished. We assume the root PCR start at context 0. We can relate Fib'1 and Fib'2 by proving the latter is an implementation of the former under an appropriate refinement mapping. In the main module of Fib'1, there is a context mapping, map1. We consider this the high-level spec. In the main module of Fib'2, there are two context mappings, namely map2 and map3. We consider this the low-level spec. In this module, we instantiate the main module of Fib'1. With map1, substitute for an expression in terms of map2 and map3. So here is the expression. This refinement works by contracting the time between the actions call and read to satisfy the behavior on the consumer action in the high-level spec. In this refinement, we have to take care of variables BP and BC of the producer and consumer. In the case of BP, we have that for in assignment, we need to keep the field R as 0, that is marked as not read, until isPrime have finished. In the case of BC, we have that for any assignment, if the corresponding BP variable has been read and is prime has finished, then the B field has to be set with the output computed by the is prime instance. So some remarks about model checking and theorem proving. We always try to make the specifications to be friendly with the model checker TLC and the theorem prover TLA-PS. Currently, we can model check properties like correctness, termination, and refinements on at least small models. If it is possible or not, it depends heavily on the problem. For very large database, simulations can be useful. We believe model checking is useful to make sure that our intuitions are correct. Currently, we have only used TLA-PS to prove type invariance, but we hope to prove correctness and refinement properties. We currently have applied the presented approach to other known problems like count words, merge sort, and end queens, but we are working on other examples also. We are missing some treatment for the PCR syntax, iterate, and feedback loop. We also are missing handle of early termination. We believe we can attempt a translation from PCR to the TLA plus, and we expect to formalize an abstract model of a target execution runtime and to prove refinements. Thank you very much.